Hi. Now in this tutorial what I want to do is show you how we can differentiate trigonometric functions such as the three examples that I've got here, and hopefully you'll be able to use these as a backdrop to being able to do similar trig functions. Now before we start, what I want to do is just remind you of three basic methods that you should already know. You'll find these documented in most formula books. If you've got y equals sine x, you should know that dy by dx is cosine x, or cos x for short. And if y equals cos x, dy dx gives you minus sine x, and if y equals tan x, dy dx equals sec squared x. Also, we can extend this. If you have got a constant in front of any function, then when you differentiate it, that constant always remains. So for instance, if you had y equals 2 sine x, dy dx would be 2 cos x. Well, let's say in general that that constant is a. So if y equals a sine x, dy dx equals a cos x, and the same is true for all of these functions. If y equals a cos x, dy dx is minus a sine x, and if y equals a tan x, dy dx is that constant a times sec squared x. So what does this mean? Well, let's just run through a few basic examples. Suppose we had y equals, say, 3 sine, not x this time, but another letter like t. Y equals 3 sine t. We can't say dy dx anymore, we've got to say dy by dt. dy by dt would be equal to, according to this rule, 3 cos t. Okay, let's try another one. Suppose we had y equals 5 cos t. Then dy by dx, oops, made that mistake, shouldn't do it, we have got no x here, it's got to be t. Dy by dt equals, according to the rule, minus that constant times sine x, minus 5 times sine x, but it won't be sine x anymore, it'll be sine t. One more example. Let's suppose we have a fraction as our constant. It doesn't matter, it's still a constant. Y equals 3/4 tan t. When it comes to differentiating this, dy by dt would be that constant 3/4 times sec squared t. Okay, so make sure you're familiar with these three functions and their differentials. Okay, so how's this going to help when it comes to differentiating my examples 1, 2 and 3? Well, you'll notice that in these examples I haven't got a single letter here as I had up here in these examples, like we had just x or just t. You'll notice it's much more than that. 5x plus 1 here, x squared plus 5 and 4x minus pi upon 2. And when you've got situations like this, you've got to turn to the chain rule. Now the chain rule is a rule that I have given you in several other tutorials, but if this is the first time that you're seeing it, I'm just going to run through this quickly for you. If you want to find dy by dx for any function, like something like this, what you can do is use the chain rule, which is basically saying that you have dy by d something, let's just put a dot there, multiplied by exactly the same d something over dx. Now this d something I'm going to call dt. You can call it any letter you like, but I'm going to call it dt. But as long as these two are exactly the same, it's as if they cancel out, leaving you with dy by dx. So this is the chain rule, and I would strongly encourage you to learn that because, as I say, it crops up so much in differentiation. Okay, so how can we apply it in these three examples here? Well, let's start with the first one, y equals sine of 5x plus 1. what we can do is change this 5x plus 1 into a single letter. Let's say we say it's t. So in other words, what we've got is y equals sine t, where t is essentially the 5x plus 1. So what have we got? Well, by the chain rule, if we're going to find dy by dx, we can say that therefore dy by dx is going to be dy by dt first of all times dt dx. Well, let's have a look at dy by dt. We've got y equals sine t, so we can easily find dy by dt. Dy by dt will be equal to cos t. So we can just write cosine there, t. But I'm not going to write the t because I know that t is 5x plus 1. So write that in brackets, 5x plus 1. Now it's very important with functions like this that you put this in its own brackets as well. Okay, so we'll put that in brackets, we'll put it in square brackets. So we've done the dy by dt bit. Now we've got to multiply by dt by dx. And we know that t is equal to 5x plus 1, so I just times it now by the differential of t with respect to x. So when we differentiate 5x, we get 5, and when we differentiate the constant 1, it goes to 0. So essentially, if we tidy this up, let's put the 5 in the front of the cosine function, and we get 5 cos of 5x plus 1. And there you have dy by dx. Let's try the next one. In this one, we've got cos of x squared plus 5. Well, we've got 3 cos x squared plus 5, but what we've got here is not a single letter. Okay, it's not a x or a t. So what we do is we create a single letter here. We basically think of this as y equals 3 cosine t, where in this example t is the x squared plus 5. So when it comes to differentiating, trying to find out what dy by dx is going to be, we can work out dy by dt first of all and times it by dt dx by the chain rule. So dy by dt, if we've got y equals 3 cos t, we know that copying this example, it's going to be minus 3 sine t. So we can write minus 3 sine of t. But t, remember, is x squared plus 5. Do put this in brackets again. So put it in square brackets. Now we've got to times it by dt dx. So differentiate t with respect to x, differentiate the first term here and you get 2x, differentiate this term and it's 0. So we've just got 2x. So put it on the end there. Now clean this up and you've got minus 3 times the 2x, which is minus 6x, and then you've got the sine of x squared plus 5. And that one's done. Now you'll notice that I've been writing my thoughts here where I've let t equal the 5x plus 1, the t equals x squared plus 5. I've written it in blue because normally I would just be thinking this and I wouldn't write this down. But I leave it up to you if you want to do that. But normally I would try and encourage you to be able to do it in your head. And in this example, I'll show you how, I'll talk you through how I think this out, okay, when I'm not writing this down. Okay, so if we've got y equals 2 tan of 4x minus pi upon 2, we're going to go straight in, get dy by dx. So we say dy by dx equals. So I think of this now as 2 tan of t. T being the 4x minus pi upon 2. So y equals 2 tan t, dy dt must be 2 sec squared t by this particular rule. So we have 2 sec squared t. I don't write the t down. I think it as 4x minus pi upon 2. So put the 4x minus pi upon 2 there. Put this in brackets, square brackets. Now I need to multiply this by the differential of t with respect to x. T, remember, was the 4x minus pi upon 2. Differentiate 4x with respect to x and you get 4. Differentiate minus pi upon 2 with respect to x. Now minus pi upon 2 is a constant, so that goes to 0. So we're just left with 4. Tidy this up and what we've got is 8 sec squared 4x minus pi upon 2. So that's how I would do it if I was not writing down my thoughts, okay? But what I'll do is I'll just put that back in, just in case you want to look at it again. What we've got is y equals 2 tan t, where t essentially was the 4x minus pi upon 2. Okay? Well, that brings us now to the end of this tutorial on differentiating trig functions like these using the chain rule. And I hope you've been able to find that helpful and can use these ideas to differentiate similar examples.